So my name is Shubham Rai, and I am PhD research scholar in Department of Applied Mechanics, IIT Delhi. So today we will be reviewing, reviewing week 6 content, and then we will solve some questions related to the lectures taught in that week. So let's start. Let me share my screen. So in week 6, you would have studied about stress strain relations. And also you would have studied about stress strain relation for isotropic material particularly. Let me have a recapitulation of the concepts that have been taught in the class. So let me see if my speaker is working. It is working. So you would have studied about linear stress chain relationships. The linear stress chain relation. So that is given by, if you remember, so that is given by sigma ij, which is stress tensor. That, and this will be related to strain tensor through a constitutive matrix. So in the lectures, sir would have applied Taylor series expansion to express stress in terms of strain, and the higher order terms have been neglected, and only the term which is linearly dependent on strains, that term has been taken. So this stress strain relationship is valid when your strains are small. So you are in the linear regime, means your stresses are linearly dependent on strains. So sigma is equal to 1 to 3, and L will also go from 1 to 3. The first term, I mean, it was the second term of Taylor series expressions. That was del sigma ij over del epsilon k multiplied by epsilon k. And this term, this whole term, can be written as constitutive matrix. So you can write sigma ij equal to summation over k and summation over L. And then you can write Cij Kl epsilon Kl. So this Cij Kl is a fourth order uh, tensor. So it is also known as constitutive tensor or stiffness matrix. So we just call it as stiffness matrix. Now, since there are four indices present in C, and there are four indices, so it's a fourth order constitutive tensor. So there are four indices I, J, K, L, and each of the indices can go from 1 to 3. Therefore, there can be 81 components in C. Okay. So, but all of the components need not to be independent. So in total, there are 81 components, but all the components are not independent. So let me just write. So we will evaluate independent components of C. You would have studied in lecture also. So independent components of tensor C. That's a four-word tensor. That's why I'm putting 400 bars here. So honestly, in total, it has 3 square 4 is equal to 81 components. So when you apply minor symmetries are applied on this constitutive tensor because stress is also symmetric and strain is also symmetric. So these two symmetry of stress and strain introduces minor symmetry in this elastic constitutive tensor. So I'm just writing here Cijkl. So that is equal to Cjikl. And this is because sigma ij is equal to sigma jl because stress is symmetric. We had derived from the law of conservation of angular momentum that stress was symmetric. Okay. So for angular momentum balance, we had done for deriving this symmetry of stress. And there is also symmetry in this KL. So this Cijkl is equal toCijlk. And this is because epsilon KL is equal to epsilon UK. This strain is symmetry. Right. So now your initially your I and J, I was going from 1 to 3 and J was going from 1 to 3. So in total, you have 9 independent components because I is going from 1 to 3, J is going from 1 to 3. So 3 multiplied by 3 is 9. But now since you have introduced symmetry, so only 6 independent components will be there because 1 2 will be equal to 2 1, 3 1 will be equal to 1 3, and 2 3 will be equal to 3 2. So only 6 independent components in IG and 6 in KN. So total 36 independent components will be left now. So you can say that after applying these minor symmetries, you have 6 multiplied by 6 is equal to 36 independent components. Then you have major symmetry also, and major symmetry comes from energy considerations. So I'm just writing it directly because you can refer to lectures if you want to go into detail of derivation of this, why this major symmetry exists for elastic constitutive metrics. But we can use this C bar MNKL. So that was expressed in terms of that was CKLMN plus CMNKL. Right? So this was the expression of C bar MNKL in the lectures. And if you see this component, so this component, if you bring this Mn in the front and KL to the last, similarly for the here, it's not going to change because I'm just doing, you can see. So first term can be written as Mn can be bring at front and KL can be shifted at the end. And similarly, in the second term also you can do the same thing. So KL can bring at front and we can shift MN at the end. Okay. So now this is equal because this KLMN is the first term and this MNKL is the second term. So it means initially we were interchanging this first two indices and the last two indices. Now we are interchanging this first two indices and last two indices combined together. So initially for minus symmetry we were interchanging individually, like if we are taking first two indices, we are interchanging IK with JN and KL with LK. But now here we are interchanging this KL, we are taking KL as one term, MN as one term, and then we are interchanging them. So this is known as major symmetry. And this exists for this C bar MNKL. So C bar, we can say that C bar MNKL, that is equal to C bar KLMN. So now you had 36 independent components. So you can write a matrix of 6 cross 6 to represent this 36 independent components. Now out of these 36 independent components, or in that matrix, where you had 36 independent components, you have symmetry. So symmetry means your off diagonal terms will be that matrix 6 cross 6 matrix will be symmetric. So you can draw a 6 cross 6 matrix and if you consider it to be symmetric, so only 21 independent components will be left now. So we can say that due to major symmetry, we can say that due to this symmetry, out of 36 components, here only 21 are independent. Okay. So we started with 81 components and then we applied minor symmetry. So on applying minor symmetry, you have 36 independent components. Then we applied major symmetry. So now you have 21 independent components. Okay. So from here we can conclude that we can just write a note here. We can say that general linear elastic material will have maximum 21 independent components. So we can say that we'll have the 21 independent material constants because this elastic constitutive matrix is dependent on material and it will be different for different materials. That's why we are saying that general elastic material, linear elastic material will have 21 independent material constants. Now we want to express stress in terms of strain using this elastic constitutive matrix. So we can say that sigma ij isCijkn and epsilon kn. But if we use void notation, in void notation we can just write, we will just write 6 independent components. If we do that, so just writing on the next page. If we do that, we will have sigma 1 1, sigma 2 2, sigma 3 3, sigma 2 3, sigma 1 3, and sigma 1 2. That is a vector. We have expressed stress as a vector in void notation. And then we have elastic constitutive matrix here. So that is 6 cross 6 matrix. We also call it as stiffness matrix. And here you have epsilon 1, epsilon 2, epsilon 3, 1, 1, 3. Sorry, omega 1, 2, 3. Gamma 1, 3. You can also express, here you have expressed stress in terms of strain. You can also express strain in terms of stress. If you do that, so strain will come here. So epsilon 1, epsilon 2, epsilon 3, gamma 2, 3, gamma 1, 3, and gamma 1, 2. If you do that, so you'll get this also will be a 6 cross 6 matrix. Here you have stresses, and here you have so this matrix is known as compliance matrix. Okay. You can stop me in between and ask me if you have any questions. So now you have 21 independent constants for a generalized linear elastic material. So that material will be anisotropic, means it will have different properties in different directions. But for isotropic materials, let's say we have isotropic material, so it will have same properties in all the directions. So there will be, instead of 21 independent components, we will have only 2 independent components left. Okay. So let me just write the stress and relationship in terms of 2 independent components for isotropic materials. Obviously, for isotropic materials, instead of, apart from this minor symmetry and major symmetry, you need to apply more symmetry. You have to apply a symmetry such that if you rotate your constitutive matrix, if you do rotation of your constitutive matrix, so it should remain same for any kind of rotation. So let's say you rotate it by 90 degree or 30 degree, 45 degree. So uh, its properties, I mean, its component should remain same because it is independent of, and this you're doing for one axis, and if you rotate it about any axis, let's say, then also its component should remain same. So this kind of symmetry you need to apply. So after doing that, so after applying symmetry for isotropic material, um, you will get stress strain relationship for isotropic material. And that is given by sigma ij, so that will be equal to lambda in trace of this strain tensor and this chronicle delta ij plus 2 mu and this strain tensor ij. So here lambda and mu are 2 independent constants that are required for isotropic material. It means you need to conduct only 2 experiments to fully characterize isotropic, linear isotropic material. Okay. So if you expand the trace of epsilon, so that will be nothing but summation of diagonal components of epsilon from the delta A plus. Okay. So this lambda and mu are also known as Lami's constants. So you will say that this lambda and mu are known as Lami's constants. Okay, Lami's parameters. Also say. So here we have expressed stress in terms of strain. Now you can do reverse also. Strain can also be expressed in terms of stress. If you solve these equations and express as strain in terms of stress, so finally you will get this. Okay, that's right. Strain can be expressed in terms of stress, and this is known as, it is called three-dimensional. It is called as three-dimensional Hooke's law. So let me write strain in terms of stress. So you will have here epsilon 1 1, so that will be 1 over E. E is Young's modulus of elasticity. Sigma 1 1 minus mu is Poisson's ratio. And obviously, you might be thinking that from where this E and nu have come. So this E and nu, actually, if you will try to, from this equation, if you will try to derive strain in terms of stress, so your expression will be in terms of lambda and mu. But certain combination of lambda and mu has been taken as E, and certain other combination of lambda and mu has been taken as nu. Okay. So E and nu are not new constants, they are in terms of this Lemming's constants only. So just to make these expressions look nice, people have used this E and mu. And this E and mu will be in terms of lambda and mu only, this Lemming's parameters. So obviously, there is a physical significance of E and nu also. That's why certain combination, combining Lemming's parameter in a certain way gives some physical significance. That's why this E and nu has been used. So what over E, not 3 minus mu into sigma 1 1 plus sigma 2. And this gamma 1 2, you will have twice of epsilon 1 2. So that is epsilon 1 2 by gamma 1 2 is obviously twice of this epsilon 1 2. And this is given by sigma 1 2 by G. You can also write sigma 1 as tau only. So and similarly this gamma 1 3, that is given as tau 1 3 by G, and this gamma 2 3. And G, this shear modulus of elasticity, will also be expressed in terms of lambda and mu. So this is known as this is tau 2 3 by G. Okay. And now I will write the expression of G in terms of G is Okay, so these are the strains expressed in terms of stresses. Now I will write these constants in terms of Lamés parameters. So G is written as E over 2 into 1 plus mu. Okay. And G is also equal to mu. In terms of Lemmy parameter, it is equal to mu. In terms of G can also be expressed in terms of E and mu, with the smallness of plasticity in the Poisson's ratio. So this I have written in terms of Lemmy's parameter also. And this nu is the Poisson ratio and it has a physical significance. Meaning it is negative of induced lateral normal strain to the applied to the imposed longitudinal strain. Means you're, let's say you have this material is let's say inelastic and you are stretching this material in this direction. So there will be some contraction in the lateral directions. So Poisson ratio is, so these contraction will be negative in the case which I'm considering. So Poisson ratio is negative of the contraction. I mean, then it will make Poisson ratio to be positive. So yeah, so it will be negative of contraction in lateral direction to the stretching in longitudinal direction. Okay, so it is kind of giving you how much lateral deformation will take place in a material when some longitudinal strain will be applied. Okay, so for a uniaxial case, you can just write as you can just write this for a uniaxial case, uniaxial loading in one direction, right? One means this is a coordinate system 1, 2, 3. So you are applying some uniaxial loading in direction one. So let's say this is direction one. So your longitudinal strain will be epsilon 1 and lateral strain will be epsilon 2. Suppose the ratio will be ratio of that one. Okay, then we have bulk modulus of elasticity. And that is denoted by this kappa. So this bulk modulus of elasticity will be given by negative of pressure applied on the wall to the volumetric strain. So this volumetric strain, you know that it is also known as, it is also equal to trace of the strain tensor, and that is equal to epsilon 1 plus epsilon 2 plus epsilon 3. Okay. And you can also write this kappa in terms of E and mu. So this can also be written in terms of Lemmes parameters finally. So so from here, actually, this bulk modulus of elasticity. So it cannot be infinity because in that case, material will be incompressible. Because whatever, so if it becomes infinity, your volumetric strain will be zero, which means whatever pressure you apply, your body is not going to have any volumetric strain, it means your body is incompressible. So that puts a upper limit on Poisson's ratio. So it means your this denominator cannot go to zero. So upper limit of Poisson ratio is 1/2. So this if we put 1 minus 2 mu equal to 0, so this mu is equal to 1/2. So that is upper limit. And lower limit comes from this shear modulus of elasticity. So this cannot be negative. So it means if you are applying a positive, let's say you're only shear stresses and strain present in a body, and if you're applying, let's say, shear stress in this direction, so strain should also be in this direction only. So with that analogy, it should not be this um, shear modulus of elasticity cannot be negative. So if it is not negative, so this 1 plus mu should be greater than 0. It means mu should be greater than -1. So it puts a lower limit on the Poisson ratio. So it means your Poisson ratio will range from -1 to 1/2, right? Actually, this cannot be infinity also. So that's why I put it as greater than -1. But a material can be nearly incompressible. That's why equal to sign is coming here. Okay, so this was the case for this was the case for linear elastic isotropic material. Now you can have linear elastic transversely isotropic material as well. So in the lectures I have told about transversely isotropic and orthotropic material. You can refer to lectures, but I'm just directly writing here that in transversely isotropic materials, there are five independent constants. So you have five independent elastic constants. Transversely isotropic materials means you have an axis of symmetry. So let's say you have some material and this is some axis. So normal to this axis in each direction, the property will be same. Okay. And along this axis, there will be some other property. So for example, if we consider these here actually, if you consider this matrix or let's say this relation, so here there will not be a single Young's modulus, there will be two Young's modulus, E1 and E2. E1 will be in this direction, and E2 will be perpendicular to this axis of symmetry. Okay. And similarly, the Poisson ratio will also be different, and this G, shear modulus of elasticity, will also be different for these. There will be two Poisson's ratios and two shear modulus of elasticity. Anyway, and for completely orthotropic material, so I think so there are five. So there will be, I think for let me just write. So I think it will be E1 and E2 will be equal to E3. That makes two independent elastic constants. And then you will have G1 2. So that will be equal to G1 3. And then you have G2 3. So 1, 2, 3, 4. And then you have some Poisson ratio. And actually, since you can express G in terms of this E and Poisson ratio, I think from there will be only five independent constants. This is 1, 2, 3, 4. And then you have new 1, 2 and new 2, 3. It's new 1, 2 and new 1, 3. So that those will be equal. And then you have new 2, 3. So these are six independent constants actually. 1, 2, 3, 4, 6. But out of these six, only five will be independent. So yeah, actually there will be one more relation. So that will be even by new 2, 1. Only five will be independent actually. If we just look, so there is some relation which is T1 value, T1 value, T1 2. So if I need to derive it, maybe you can look to one book. So yeah, so these are the constants that I have written, but out of these six, only five will be independent. So if you want to have complete derivation, you can look to a book by Martin H. Saar. It is title is I think theory of elasticity. Okay, so in that sense, but it is a book for Ajit sir also has written a book, so it is also a very good book for undergraduate. But this Martin is said is a book for postgraduates, so you can only see the things which are relevant to your understanding. Anyway, okay. So now you have orthotropic materials. In these materials, you have nine independent constants. Okay. Then we will go to problems. So obviously in orthotropic materials, the properties in all the three directions will be different. So I think here nine independent constants will be E1, E2, E3, G12, G13, G23, and nu12, nu13, nu23. Okay, so these will be nine independent constants. Okay, so let me go to the problems. Problem one. I'm starting with problem one. So let me just write what is the problem one. So problem one is think of a rubber cube which is inserted within a cavity in steel block. The cavity has same form and size as that of rubber cube, and this will be shown below. The top surface of rubber cube is pressed by another steel block. With a pressure of P. Pascals. And you have to assume the steel to be rigid and that there is no friction between steel and rubber. Okay. So what you need to find out is, so you have a rubber cube which is inserted within a cavity in a steel block. The cavity has some form inside as that of rubber cube. The cavity is same form, has same form and same size as that of rubber cube. And top surface of rubber cube is placed by another steel block with a pressure P pascals. You have to assume the steel does not go any deformation, it is resin, and there is no friction between steel and rubber. And what you need to find out is in part A, you have to find the relationship between normal stresses in x and y direction in this problem. And in part B, you have to find the volumetric strain. Okay. So if you draw the diagram, so diagram is something like this. You have okay, so and this is the pressure that has been applied on the steel block, and this pressure is P. And this is uniform, okay, uniform across this length L. And this is rubber, and this is C. Okay. And your coordinate system are is like this. So this is your y-axis, this is your z-axis, and this is your x-axis. So now can you try to solve this? Just giving you 2 minutes. You have to find the relationship between normal stress in x and y direction in this problem. So how will you proceed? First, you try to write the displacements. So here, the displacement in x direction, so that will be zero because your rubber block is in a cavity. So it cannot go displacement in x and y direction. So there will only be displacement in z direction. And displacement in z direction will be a function of z only because your pressure here is uniform. Pressure is not varying with respect to x and y. So that's why your deformation in z uh, will be function of z only. So you can write ux is equal to 0, uy is equal to 0, and uz is a function of z. From there, you can find, if you find strain tensor will have all the components 0, and only epsilon zz will be present. Yeah. From there, you can just try to find out the stress tensor using elastic constitutive matrices, or this is a linear elastic material. So When we are assuming it to be linear elastic material, although rubber is a hyperelastic material, but we are assuming it to be linear elastic, so we are assuming the stresses, I mean, strains are small, so it is in the linear elastic region. Okay, so let me solve. So solution. The solution is we are saying that ux is equal to 0 and ui is equal to 0 and uz could be function of x, y, z, both, all three, but here uz will be a function of z only. I mean, ux, y, z, uz will be a function of z only. So we are saying that uz is a function of z. Because here the pressure is uniform, it's not varying with x and y. If it will vary with x and y, it will introduce some gradient of the displacement with respect to x and y. But here it is uniform, so it will not introduce any gradient. So that's why you will be function of z only. Anyway, so stress tensor, how we can write stress tensor components. Sorry, it is strain tensor, not stress. Strain tensor components. So if you try to write this, so you will only epsilon zz will be zero, rest will be only epsilon zz will be non-zero, rest will be zero. You can just try to find out. Very easy because the first component is del ux by del x, so that is zero. Here you have half of del ux by del y plus del uy by del x. So ux and uy both are zero. Here you have half of del ux by del z plus del uz by del x. So del ux is zero and del uz by del x. So uz is not a function of x. This will also be zero. Similarly, all these terms will be zero. So from using this Hooke's law, this three-dimensional Hooke's law, you can just find, you can just say that your tau xy was, so from this strain matrix, we can say that your epsilon xx is equal to epsilon yy is equal to epsilon, epsilon zz is no more, so epsilon xy is equal to epsilon yz is equal to epsilon xz. all will be zero. Only non-zero component is epsilon. Obviously, I should write it as capital A. This is non-zero. So from here, from Hooke's law, you can conclude that since your tau xy is nothing but g into gamma xy. Gamma xy is nothing but twice of epsilon xy. So epsilon xy is zero, that's why this will also be zero. So your tau xy is zero, and then similarly your tau xz, that will also be g into gamma xz, and your gamma xz is zero because your epsilon xz is zero, so this will also be zero. Then you have tau yz, so that should be equal to g into my gamma and nu both should look different. Okay, gamma yz, so that should be equal to zero. These stress components are zero. And we can also say that your sigma xx will be equal to sigma yy because here there is a symmetry, and from xx and yy you have same boundary conditions, and you do not have any external traction in xx and yy direction. Boundary conditions are also same, that is the block cannot move in x or y direction. So we can say that sigma xx is equal to sigma yy because direction and y direction will experience equal reaction forces, and those reaction forces will lead to traction and then normal stresses. Same traction, same normal stresses. So sigma xx will be equal to sigma yy, and this will be equal to, I mean, this two will be equal. So we can just write the expression of epsilon xx from three-dimensional flow. So epsilon xx is nothing but 1 over e, and this is sigma xx minus nu into sigma yy plus sigma zz, right? And from here we know that sigma xx is equal to sigma yy. So here we can just put sigma xx also. So we will be left with, so you can take sigma xx as common. So this will be sigma xx times 1 minus nu plus, I mean, minus nu times sigma zz. So sigma xx that we will get will be e times the split. Okay, also this epsilon xx is also zero. So from here you can say that this expression is equal to zero because your epsilon xx is zero from the strain matrix, strain tensor. So then we can definitely say that sigma xx, uh, because we had taken 1 minus nu as common, so it will be nu times sigma zz over 1 minus nu, right? If I'm not wrong, you can just try to get this. So in my grammar animation, okay. So this you have got, and the expression of sigma xx, and this will also be sigma yy. So now you have to find a relationship between normal stress in x and y direction in this problem, right? So normal stress in x and y are equal, but that you have to express in terms of z, sigma zz. So this we have done. Now let's find sigma zz. So for that we need to find out. So this traction on this top surface that we need to find out. This top surface. So this is the top surface of the rubber, right? And let's say this height of this steel block is h, and density of the steel block is rho. So due to gravity, it will exert a pressure, and area of it will exert a pressure of rho gh, right? So and there is external pressure P as well. So total pressure on this red line or this upper part of the rubber block will be P plus rho gh. So I'm just writing here. Traction on top face is equal to external pressure plus weight of the steel block. Pressure due to weight of the steel block. Top face of rubber and the writing clarity. So we can just write on the top face. So let's say we have a stress tensor and we want to get traction on face E3 because this face here will have normal component. Normal of this face will be in direction E3, so we want to get traction on this face. So that's why we are noting sigma n. Not it will not be a dot product, but rather multiplication of stress tensor with normal vectors. That will be sigma E3. This will give you traction on face of the rubber. So that is nothing but P plus rho GH. That is pressure. I mean traction is force over area, so that is pressure, and that is in minus E3 direction. So this is the traction on face E3. So if you expand this, this will be nothing but third column of this stress tensor. So if you do that, so this will be third column. So this will be xz, sigma xz, sigma yz, and sigma zz. Right. This is the vector that you will get, and that should be equal to this. This is E3, so positive components will be 0. So 0, 0 minus P plus OH. From here, you can conclude that, and we had derived also that sigma xz, sigma yz are 0 on top face. And because we had derived that this will be 0 everywhere, so it will be 0 at top face also. And here we have only sigma zz present. Sigma zz minus P plus OH. Okay. So now we can substitute the value of sigma zz in this. Let's say this is equation number 1. Substitute in equation 1. If you do that, what will you get? So you will get sigma xx, and that is also equal to sigma yy. So that is equal to minus mu over 1 minus mu. And because here you have mu over 1 minus mu, minus is coming from this sigma z and e plus whole cubes. Finally, you have moles. And then now you can derive epsilon zz. So in the next part, you need to. So we have found out the first part, the relationship between normal stress in x y direction in this problem. So that is, we had to find the expression of normal stress in terms of this pressure, or expression of this sigma xx and sigma yy in terms of this pressure that we have done. And now we have to find volumetric strain. So for volumetric strain, we need epsilon xx, epsilon yy, and epsilon zz. And we have epsilon xx and epsilon yy as 0. So we need to find epsilon zz now. Epsilon zz is nothing but 1 over e from 3-dimensional Hooke's law, sigma zz minus mu times epsilon xx plus, sorry, sigma xx plus sigma yy. Obviously, all these x and y should be capital and this writing. 1. So these all are equal. So yeah, sigma zz is will remain as it is, sigma zz minus this new into sigma xx plus sigma yy. So sigma xx and sigma yy are equal, so it will be 2 new sigma xx. If you put the values now, so it will be 1 over sigma zz. So here I'm putting equation number 1. So it will be 1 over sigma zz, and sigma xx will be expressed in terms of sigma zz again from here. So you will get minus 2 new and just mu square sigma zz over 1 minus mu. Because sigma xx is new times sigma zz over 1 minus mu. So and then you can take sigma zz as common, so you'll get sigma zz over e 1 minus 1 mu square over 1 minus mu. So this is the expression for x from z. Now we can find volumetric strain. So if you try to find your volumetric strain now, so that will be nothing but epsilon v, and that is trace of, that is, you know, that is trace of strain tensor, and that is given by epsilon xx plus epsilon yy plus epsilon zz. Okay, so I'm going to substitute epsilon xx and yy are 0, epsilon zz is given above, so epsilon zz is 1 minus 2 mu square over 1 minus mu times sigma zz over 2. And you can substitute the value of sigma zz. So sigma zz is minus p plus rho gh. So this will be minus of ms. I'm checking LCM. So it will be 1 minus mu minus 2 mu square over 1 minus mu. And sigma zz is minus p plus rho gh. This will be the final expression for 1 minus 2. So this rubber, if we consider this to be a linear elastic material, will experience volumetric strain, and due to Poisson's effect, there will be stresses in x and y direction as well, and there will be stress in z direction also. So the z direction stress is simple; it will be minus p plus rho gh, and sigma xx and sigma y will come from the Poisson effect that you derived, and there will be volumetric strain because this rubber will get compressed. Okay, so let's go to the problem number 2. Problem number 2 is you have to think of a rectangular plate being compressed along the four edges, but not allowed to expand or contract in its thickness direction. So in its thickness direction, it's not allowed to expand or contract. Means uz is 0. There's no displacement in thickness direction. So you have to assume the thickness direction is around z direction. Zx is equal to. It's also given that the following components of stress and strain matrices are given. So those are sigma xx equal to sigma yy is equal to minus p and tau xy is equal to yz is equal to tau zx. That should be 0. And your epsilon zz is also 0. This has been given to you because epsilon zz will be 0 because there is no information allowed along thickness direction. So that's why it will be 0. So you have to assume the material to be isotropic and to find out the remaining components of the stress matrix. Okay, so it's been given to you that you have a rectangular plate being compressed along the four edges, but not allowed to expand or contract in the thickness direction. The components of stress and strain matrices are given that sigma x and sigma y is equal to some pressure minus p because the plate is compressed uniformly along the two directions, and all the shear strain will be 0. Shear stresses will be 0, and strain in the direction is given to the plate. If you assume the material to be isotropic, you have to find the components of remaining components of stress matrix. So it means uh, actually you have to find the remaining components of strain matrix because stress matrix, all the components, almost all the components have been given. Anyway, so let me draw the plate. So let's say you have this kind of plate. Okay, so you have this kind of a plate and uniform pressure is applied like this from here also and here also. On this side also and from this side also. And your coordinate system is, let's say you have this y, along here you have x, along the direction you have z. So it's been given to you that uz will be equal to 0, and that's why epsilon zz will also be equal to 0. So you have to find epsilon xx, epsilon yy, epsilon xy, I mean gamma xy, and gamma xz, and gamma yz. These components you need to find. So you know that gamma xy is nothing but g times tau xy divided by g, right? So that's why this will be 0 because tau xy will be 0. And gamma x, similarly, gamma xz will be equal to gamma yz, and these two also be equal to 0 because this all these stresses are also 0, so strains will be 0 from the considered relation. And now you have since your epsilon zz is 0, so epsilon zz in terms of, if we write in terms of stresses from three dimensional flow, so this will be sigma zz minus mu times sigma xx plus sigma yy. Since your sigma zz is 0, so and this is equal to 0, so we can say that your sigma zz, so that is equal to mu times sigma xx plus sigma yy, right? And your sigma xx, obviously, here, if you see from here, your sigma xx is nothing but minus p, and sigma yy is also minus p. Here it is given to you, so it is negative of pressure. So we can say that from this expression, we have minus 2 mu and p. Okay. So you have now your sigma xx, oh, sigma zz also. Now you need to find out epsilon xx, because all the components you have found this gamma xz, gamma yz, gamma xy, and you find and your epsilon zz is 0. So sigma zz you need for this finding epsilon xx and epsilon yy. That's why we have found out sigma zz. So that will be in terms of sigma xx and sigma yy only, because epsilon zz is 0. So since I believe that plate would have been free in z direction, there wouldn't have been any stress. But now you have restricted the plate in z direction. It means when you are pressing it from x and y direction, the plate will try to bulge. Plate will try to expand from z direction, but we are not allowing it to expand. So there will be a compressive stress that will be developed, because it has to expand, but you are not allowing it to expand. Means there is some compressive force acting on the plate that is restricting the plate to expand. That's why this compressive force is emergent. Now you have epsilon xx equal to 1 over e xx minus nu times sigma zz plus sigma yy, right? So now you have expression for everything. So we just put it here. Sigma xx is minus p minus mu times sigma zz is minus 2 mu p, and sigma yy is minus p. If you solve it, you will get minus. I'm just taking p as common. So here you can get minus p by e, and the expression that will be left with here, you will have 1 plus, and you have here mu times 2 mu plus 1. Here will be minus because you have taken here minus minus will be plus, and you have taken minus as common, so here it will be minus. Final expression will be this only. And your epsilon yy is again this 1 over e sigma yy minus mu times sigma xx plus sigma zz. So you get again, you get the same thing, minus p by e. You substitute the value, you get the same thing because you have same forces for x and y direction. So 1 minus mu times 2 mu plus 1. So now we have found all the components of strains that we had to find out. So we have found sigma xx, sigma yy, sorry, epsilon xx, epsilon yy, gamma xy, gamma xz, and gamma yz. So that's what we needed to evaluate in this question. Let me go to the next question. You can stop me in between if you have any doubt in any of the questions. Let me go to problem 3. So you have to show that in case of isotropic bodies, the stress tensor and strain tensor will both have same set of principal directions. Okay. So and also you have to discuss, I mean, not discuss, you have to further show that the set of planes whose normals are parallel to one of the principal directions do not slide related principle. Okay. You have to show that in case of isotropic bodies, the stress tensor and strain tensor will both have same set of principal directions. You will further show that set of planes whose normal are parallel to one of the principal direction do not slide related to each other. Second part is easy because planes parallel to the principal directions will not have any shear strains, and if they do not have any shear strain, they will not slide related to each other because in one of the lectures, sir had discussed that shear strain essentially means sliding of plane one over the other. But since shear strain will not be there on the planes whose normals are parallel to one of the principal directions, so shear strain will not be there. So there is no shear strain, there will not be sliding. So essentially, we need to only show the first part. So let me do the solution. So it's kind of eigenvalue problems. Firstly, let's find out the principal directions of string tensor. So eigenvalue problem for string is because it boils down to eigenvalue problems when we try to maximize the normal component of the strain, normal component of the strain tensor or stress tensor. It boils down to eigenvalue problem. Where eigenvalues are the principal values and eigen vectors are the principal directions. So let's say you have the strain tensor. So I'm deciding eigenvalue problem. So sigma n, I mean epsilon n is equal to alpha n. So this n is eigenvector, and this alpha is eigenvalue. So this will also be principal value. Okay, and this will be principal direction. And since for isotropic material, we can write, so for isotropic principal value of strain component, we can say that principal direction of strain. And for isotropic materials, let's write the relationship between stress and strain. So stress is given by lambda times trace of strain tensor. Let me just write it firstly without multiplying with n. So this is given by sigma is equal to, for isotropic materials, stress strain relation is, so this is given by sigma is equal to lambda times trace of strain tensor. Right? So it is given by sigma is equal to lambda times trace of strain tensor times identity matrix plus 2 times strain tensor. So what you have to do is, since you want to solve eigenvalue problem, so you need to multiply with the principal direction. So that is eigenvector. So, so I'm just post multiply the above equation with principal strain. Principal strain normal. And why we have multiplied it with principal strain normal? Because we want to show that the eigenvalues and eigenvectors or principal directions of stress and strain for isotropic material are same. That we want to show. So since we want to show that stress and strain tensor will have same principal direction, that's why we have multiplied this equation with the principal direction of strain. And then we will show that indeed this is the principal direction of stress as well. Okay, so let's first multiply. So it will be, so and we have post multiplied means n will be multiplied after sigma. So and on the right hand side also, so it will be lambda times trace of epsilon and I and and plus 2 mu times strain tensor times n. Right, so this is post multiplication of n with in this equation. Now if you try to see, so this is nothing but lambda times, so trace of epsilon is an invariant. So it doesn't matter in which coordinate system you take, it is going to be same. So otherwise, yeah, so it is an invariant. So it doesn't matter whether you take in XYZ coordinate system or principal coordinate system, it's going to be same. So that's why now I'm assuming that it is a principal coordinate system. So principal coordinate system of strain. Obviously, this is trace of epsilon. So this will be summation of principal values now because of fragment terms will go to zero in the principal coordinate system. And this I times n will be n only, thus 2 mu. Epsilon n is, we can write if n is a principal direction. So epsilon n will be alpha times n, right? And here I can replace this. So alpha times n, where alpha is the principal value of the string. Okay, so I have used this equation here. So now I can write it like this. Now I can take n as common. So if I take n as common, lambda times trace of epsilon plus 2 mu alpha times n that you are getting. And if you see, this is nothing but principal value of stress. Why? Because this is principal strain, because summation of principal strain. Yeah, this will be summation of principal strain. And this is a principal strain itself, one of the principal strain itself. So, so this is principal strain. So this will be the so only principal strains are involved in this equation. That's why the stress will also be principal stress value. Value will also be principal stress. And it boils down to be a, I'm telling it why. This is because let's say that this whole term is a scalar only. And because this is also a scalar, this is also a scalar. So if let's assume it to be beta. So you can write like this as sigma n is equal to beta n, right? So it's again a eigenvalue problem. So that's why this n will correspond to principal direction of stress. Which is equal to principal direction of strain because n initially we had taken as principal direction of strain. Directions. And now beta is principal values of stress corresponding to each principal direction. There will be a principal value, and that is given by lambda times. That is coming from the constitutive relation itself. If we just substitute principal strain in the constitutive relations. So lambda times trace of epsilon. So we can assume now here trace of epsilon doing principal coordinate system is not going to change, it's invariant, plus 2 mu alpha. Alpha is the principal value of the strain. Okay. So now therefore we have proved that for isotropic materials, the stress and strain have same principal directions. Okay. So I'm just writing here. It's mutant. So we can see that N also turns out to be principal direction for stress vector for stress tension. Okay. So let me go to the next question. So that is question number 4. You can stop me and ask if you have any questions, any doubts. The question number 4 says the sample is subjected to a biaxial test under plane stress conditions. That is sigma xx is equal to rho xz is equal to rho yz equal to 0. So it is subjected to biaxial test and condition is plane stress means out of this will be sigma zz I think. All out of plane stresses will be 0. Okay? And it is subjected to biaxial test using a special loading frame that maintains an in-plane loading constraint. And what is that constraint? And constraint is sigma xx is equal to price of sigma y. Okay. And what you need to find out is in part A, you have to find the slope of sigma xx versus epsilon xx. In the second part, you have to find the ratio between epsilon xx and epsilon yy in terms of Poisson ratio. In terms of mu. And in the last part, you have to find the ratio between epsilon zz and epsilon xx. You have to find the ratio between epsilon zz and epsilon xx. Okay. So a sample is subjected to a biaxial test under plane stress conditions using a special loading frame that maintains an in-plane loading constraint. Constraint is that sigma xx will be double of sigma yy, and you have to find the slope of sigma xx versus epsilon xx. You have to find the ratio between epsilon xx and epsilon yy in terms of mu, and you have to also find the ratio of epsilon zz and epsilon xx. So let me write the solution. Again, let me draw the plate. So plate is something like this only. So here you have been applied a load in this direction, a load in this direction. And now you have here you have x, y, and z. So let me write the firstly you have to find the slope of sigma xx and epsilon xx. So let me write the expression of epsilon xx. Epsilon xx is given by 1 over e sigma xx minus mu times sigma yy plus sigma zz. So, and it's given to you that sigma zz is 0 here. So you just put the value of sigma zz. So you put that, so you will get 1 over e sigma xx. So you can just divide with sigma xx also, because there is a ratio between. So you need to find out the slope of sigma xx and epsilon xx. So I'm just finding the ratio of epsilon xx and sigma xx. So I'll get the slope also. So epsilon xx over sigma xx. So that will be given by, so this will be 1 minus mu times sigma yy over sigma xx, right? And sigma zz was 0. So this has been substituted as 0. So if you now solve this, so you will get, so this is 2. So you will get epsilon xx over sigma xx is equal to 1 over e, and this is nothing but 1 minus, yeah, 1 by 2 mu by 2, right? So finally, if you express sigma xx is nothing but e over this mu by 2 over minus 2 mu this way. Sigma yy is sigma xx is twice of sigma yy. That will be should be 1 by 2. Yeah, it should be 1 by 2. Okay. And with 1 minus mu by 2. Right. So this is the relation that you are getting between epsilon xx and sigma xx. I mean, yeah. So slope is nothing but, so slope between sigma xx and epsilon xx, can just say that slope between sigma xx and epsilon xx is nothing but, so 2, I'm just taking the LCM, so it will be 2 e over 1 minus 2 v, right? So this will be the slope. Now let me just verify once more. So I think this sigma xx is equal to twice of sigma yy. Uh, so minus, okay, it's fine. Okay, so now this is fine. So we have to find, so we have found out the slope between sigma xx and epsilon xx. Now we have to find the ratio between epsilon xx and epsilon yy in terms of mu. So we need to evaluate epsilon xx divided by epsilon yy, right? That we need to find out. We already have epsilon xx over sigma xx. So if we find sigma xx over epsilon yy, then we can multiply these two equations and then get epsilon xx over epsilon yy. So let me just write epsilon yy. So that will be 1 over e. So this will be sigma xx, sigma yy minus mu times sigma xx plus sigma zz, and sigma zz is 0. So I'm just dividing it by epsilon x. So I'm just dividing it by sigma xx. Okay. If you do that, so you get 1 over e sigma yy over sigma xx minus this mu, because sigma xx over sigma xx will be 1 and this is 0. And it's been given to you that sigma xx is twice of sigma yy. So again, here you will have 1 over 2. So you can say that from yy over sigma xx. So 1 over 2 minus nu, right? So from here we can say sigma xx over epsilon yy. So that will be equal to 2 2e epsilon yy over 1 minus 2 mu. So this two will be same. Uh, mm, yeah, so that's a mistake. Okay, that is fine that it is 1. But here there will be 2, right? Because if we take LCM, so this will be 2 minus 2 and then it will be 2. Now here it will be 1 minus 2 nu by 2. So that's why 2e over 1 minus 2 nu that we get. And here it will be 2 minus nu by 2. Right? Now it's fine. Yeah. So let me just multiply. So let's say this is equation number 1 and this is equation number 2. So if you multiply equation with the equation 1 with equation 2, so you will get epsilon xx over sigma xx multiplied with epsilon, so that is sigma xx over epsilon yy. If you do that, what will you get? If we solve this, very simple. So you just put the value. So you get 1 over e. So this expression here is, I'm putting here sigma xx epsilon xx over sigma xx. So this will be 1 over e 1 minus nu by 2. So that is 2 minus nu over 2, right? And then multiplied with, I'm using this expression here. So equation 1, I'm referring to this equation. Equation 2, I'm referring to this equation. Okay. If you multiply it, so you get 2e over 1 minus 2 nu. Yeah, that's all I think we should. Okay, so e and e will get cancelled. So you get epsilon xx over epsilon yy as e also will get cancelled. So 2 minus nu over 1 minus 2 nu will get finally. Okay, so that's the ratio between epsilon xx and epsilon yy. So let me go to the next part. So now you have to find the ratio between epsilon zz and epsilon xx. So do that means you have to find epsilon zz over epsilon xx. So you have sigma xx over, I mean epsilon xx over sigma xx, or we can say that sigma xx over epsilon xx. I'm just writing this expression again. So one equation that I have is sigma xx over epsilon xx. So that is nothing but 2e over 1 minus 2 minus nu times, yeah, that is there. So that is the ratio between sigma xx and epsilon xx. Now you need to find out this ratio. So if I have epsilon zz over sigma xx, then I'm able to multiply these two equations. So let me, I'm just naming it as equation number 3. And I'll just write epsilon zz, so that there is nothing but 1 over 3. And that is sigma zz minus mu times sigma xx plus sigma yy. And sigma zz is 0, so it will be 1 minus mu. So it will be minus mu. And it's given to you that sigma xx is equal to twice of sigma yy. So this will be 3 times sigma xx. Right? So, so you are getting epsilon zz over sigma xx is equal to minus 3 mu over e, right? If you multiply 3 times 4, what will you get? So sigma xx and sigma xx will get cancelled, so you will get epsilon zz over epsilon xx. So that is nothing but 2e over 2 minus mu times minus 3 mu over e. So e and u will get cancelled, so you get minus 6 mu over 2 minus mu. Okay, so this is an answer. This is the final answer. Right? So now we have found out the ratio between epsilon zz and epsilon xx also, and epsilon xx and epsilon yy also. Now let me once more check this one because I have some different answer for this question. Or maybe earlier I had committed some mistake. Let me just recheck. I think this calculation is correct, but let me just recheck. It's very simple. So this is fine. So sigma xx is twice of sigma y1. 1 by 2. So this will be 0 minus 2 mu by 2. This is fine. Now the above equation is fine. So this will be 2 minus mu by 2. So this is also fine, I think. And then when I'm multiplying, so epsilon xx over sigma xx. So that is 2 minus mu by 2 e. And then we have sigma xx over epsilon yy. We have 2 e over. So yeah, this is fine. It's correct. And then I have here something. So 3. And then I have this expression. So I'm just multiplying this expression with this one. So sigma xx will get cancelled. Epsilon zz over epsilon xx. Okay, yeah, this is fine. Earlier I would have, I think I have some wrong answers beforehand. Okay, so let me go to the next question. So it is problem number 5. It's the last problem of this session. These calculations are simple only. You just need to pay a bit attention. And here, from these questions, you will get to know how to apply the concepts learned in the class. So let me quickly do this problem, write this problem. So the problem is you have to think of an isotropic square plate which is clamped along one of its edges and subjected to uniform normal compressive load. Uniform normal compressive load, right? On the edge opposite to the clamped edge. Opposite to the clamped edge. The other two edges are free. Are traction free. There's no traction. Suppose that no out of plane displacement generates. There's no out of plane displacement. Furthermore, the displacement components ux and uy are not functions of z. Either. Okay. So what you need to find out is you have to write down the strain and stress matrix for the problem. First part is this. Second part, you have to show that z component of stress equilibrium equation is automatically satisfied. You have to show that z component of stress equilibrium equation is automatically satisfied. Okay, and finally, you have to show what boundary conditions will be used to solve the deformation problem. You just have to show the boundary condition. You don't have to solve. You have to show that what boundary conditions will be used to solve the deformation problem. Okay. You have to think of an isotropic square plate which is clamped along one of its edges and subjected to the uniform normal compressive load on the edge opposite to the clamped edge. The other two edges are traction free. Okay, so let me draw the diagram first. So this is solution. Diagram looks something like this. So let's say you have Let's say you have this plate. Okay. And it's clamped at this edge. From here it is clamped. And there's a full force friction that is applied here. And let's say this is P. So I'm saying that let's say this is side one, side two, side three, and side four, and coordinate system here is, so this is direction Y, this is direction X, and this is direction Z. Okay. Obviously this is X, and here you have Y, and obviously here you have Z. Okay, so it's given to you in the question that deformation are not a function of Z, and there are no out of plane displacements allowed. So out of plane is not allowed. It means you have uz equal to 0. And also ux is a function of x and y only. And uy will also be a function of second function of x and y. So in the first part, you need to find the component of stress and strain tensor. So I'm just finding firstly the component of stress tensor. If you do that, so that will be given by this is stress. Let me, instead of stress, firstly let me find the component of strain tensor. So component of strain tensor will be mostly first component is del u x by del x, and second epsilon xx, the epsilon xx is given by del u x by del x, epsilon xy, so that is half of del u x by del y plus del uy by del x, and this third component will be zero because del ux, it will be del ux by del z, which is ux is not a function of z, so that will be zero, plus del uz by del y, so that will be zero because uz is zero. Then this will be symmetric, so this will be same as 1 to del ux by del y plus del u by del x. And here you have del uy by del y, right? And this will be zero, this will also be zero. This will be zero because here you will have del u. So this is 2, 3. So here you will have del u y by del z, which will be 0, plus del u z by del y. Z is 0. Right. Okay, because uy is not a function of z, so that's why this will be 0. And here, since uz is 0, so differentiation of uz with respect to the u will be 0. So this is 1, 3. So this symmetric matrix. So this will be equal to this one. This will be equal to this one, and del uz by del z will be 0. The whole strain matrix now we have. So actually, if you see, you only have in plane strain components, all out of plane strains are zero. So this condition is known as plane strain condition. Let me just write. So this condition represents plane strain condition. Therefore, all out of plane components, all the components associated with out of plane directions, associated with out of out of plane directions are zero. So that is, we can say, I mean, you can just figure it out. So that all out of equilibrium and below. Actually, you can compare this with, here we have epsilon xx, epsilon xy, and xz. So epsilon yx, epsilon xy and yx are 0, epsilon yy, and epsilon yz. And here we have epsilon zx, epsilon zy, and epsilon z. Compare from here. Anyway, so let me solve this. Okay, let me find the stress matrix also. So stress matrix now, so that will be given by, so if you see here that is, it is very clear from here that there will be no stress in, so let me just write. There's no out of plane displacement, and the displacement components are, so if you try to write the stress matrix, how we can write it? Um, yeah. So since this out of plane strain is zero, so epsilon xz is zero, so gamma xz will also be zero, and gamma xz. So tau xz is g times gamma xz, so this will also be zero. So here also there will be zero strain. Here also similarly there will be zero. And here the zero stress. Here also there will be zero stress. All the out of plane shear stresses will be zero because there is a direct relation that tau xz is equal to g times gamma xz, tau xy is equal to g times gamma xy, tau yz is equal to g times gamma yz. So since xz, yz, and zx are zero, so corresponding stresses will also be zero. Rest other stresses will be present, so I'm just writing here sigma xx, sigma yy, sorry, sigma xy, or you can just write tau xy. Here also it is simple, so this will be tau xy and tau yy, and there and sigma y, and here we have sigma z letters. If you try write in terms of Lami's constant, so if you remember the relation, we just use that. So it will be lambda plus 2 mu epsilon xx plus lambda times epsilon yy, and this will be 2 mu epsilon xy. This will be 0. And here again you have 2 mu epsilon xy because this is symmetric. And here you have lambda plus 2 mu. You just use the Lami's in the relation between when the stress will be expressed in terms of strain using Lami's constants. If you use that relation, you will get this expression. So this will be 0, and this will be 0, 0, and this will be lambda times epsilon xx plus epsilon y, because epsilon zz is 0. Okay. Now, so we have now the strain tensor and the stress matrix, strain matrix and the stress matrix. Now we need to find out in the second part, we need to show that the third equilibrium condition is automatically satisfied. So that component of stress equilibrium equation. So that component of stress equilibrium equation is given by tau del tau zx by del x plus del tau zy by del y plus del tau del sigma, we can say that del sigma zz over del z plus some body force. So there's no body force here equal to, again, this will be 0 plus some body force equal to some acceleration. So this is a steady problem. So there will be acceleration. So that will be 1. So obviously this will be mass index solution. Anyway, so now we see that this del tau zx is 0, so this will go to 0. Tau del zy is 0, this will go to 0. And now we have del tau del sigma zz over del z. So if we substitute the expression for sigma zz, so that is lambda times epsilon x6 plus epsilon y, right? Over del z. So that we need to show that it should be 0. And indeed, this is 0 because epsilon xx and epsilon yy are functions of x only. Because epsilon xx, if you see, that is del ux by del x, and epsilon yy is del u by del y. So ux and ui are function of x and y only. They are not function of z. So that's why epsilon xx and epsilon yy will also be function of x and y only. So that's why this differential will also be closed because this is not a function of z. Epsilon xx and epsilon yy are not a function of z. This differential will also be closed. So you see that the z component of stress equilibrium equation is automatically satisfied in plane strain conditions. So LHS is equal to OHS. So we can say here that since epsilon x6 and epsilon yy are functions of are not functions of z, are not functions of z. So stress equilibrium equation for z direction is automatically satisfied. For plane strain conditions. Now in the third part of the question, you have to find you have to write what boundary condition will be used to solve the deformation problem. So boundary conditions for this is that on this edge here, so this edge is corresponding to x is equal to 0 and y and z can be anything. So at x is equal to 0, or ux and uy will be 0 and uz is 0 everywhere anyway. X is equal to 0, x and uy will be 0. And at x is equal to L. So if you consider this to be um, length L, if you consider this plate has length L. So at x equal to L, you can say that the traction component. So traction component will have direction minus p. So traction component in x direction will have a value minus p here. And here on phase 2 and phase 4, the traction are 0. Right? So phase 2 has a normal component E2 and phase 4 has a normal component minus C2. So on these phases, traction will be 0. Here, this normal component is E1. So here the traction will be minus p. And here the displacement will be 0. So let me write these four boundary conditions. So let me solve part C. The displacement and traction boundary condition that will be used to solve this problem are as follows. So let me first write displacement boundary condition on phase one. There are four phases, so there will be four boundary conditions. So we say that ux at x is equal to 0, right? So we say that x is 0 and y and z could be anything. So here this should be 0. And uy at x is equal to 0 and y and z could be anything, but they should also be equal to 0. So this is the displacement boundary condition on phase one. And since phase two is traction free, so traction boundary condition on phase two, and phase two has a normal vector E2. So we say that sigma stress tensor at that point and E2, so this should be equal to 0. I would say that this is phase two. So this is nothing but second column of the stress tensor. So this is tau xy. So yy sigma yy and so zy, right? So this should be equal to 0. So all three should be equal to 0. Remember, we need to solve stress equilibrium equation. Third stress equilibrium equation is already satisfied. Only first two stress equilibrium equation need to be solved. And for that, we need some boundary conditions because there are only two equations and we have six stress components. So we need more equations. Okay. So we'll use these boundary conditions for solving. So fraction boundary condition on phase three. So phase three has a normal E3. So sigma, sorry, normal E1. So sigma E1 in phase one, phase three. So that will be first row of stress tensor. So this will be column of stress tensor, sigma xx, sigma yx, and sigma tau yx. So it's and tau zx. So that should be equal to, that is only minus p in x direction, and in y and in the shear, there is no shear traction here. So these are 0. So from here, we can say that sigma x is minus p, tau yx, and tau zx are 0. Similarly, traction BC, traction boundary condition on phase 4, there should be sigma times, and phase 4 has direction minus E2. So you can also write that it is minus times sigma E2. And this is phase 4. It has a normal, plane normal as minus E2. So you see, this is nothing but sine column of stress tensor. So this is minus of tau xy and minus of sigma yy and minus of tau zy, right? So these are all three answers. Okay, so these are the boundary conditions that we will use for solving this problem. So we will stop here for today. And if you have any doubt, you can post in the discussion session or YouTube. On YouTube also, you can post actually in the comment section. Okay, so we will meet in the next class. Thank you for your attention.